Hi, my name is Josh Wheeler, and I'll be explaining today in this video how to derive a van der Waals equation dealing with A and B parameters in the terms of critical temperature and critical pressure. And we will be looking at the critical point of substances along with dealing with the compressibility factor and how its relevance is to the van der Waals equation of state. Okay, so I'm going to bring you over here. We're going to take a look at this chart real quick, or this plot, looking at the various states, the solid phase, liquid phase, and the vapor phase. And we want to ask ourselves and look at this, and I want to make a note that every compound or element has a certain point, has a critical temperature and a critical pressure. It is a point where after you go to that point, you're in a critical zone. So a critical point is when you have a critical temperature, so a temperature that goes past its critical point, and also past its critical pressure point. So you have this point right here, where your critical pressure and critical temperature are both past those certain points. You have a critical point. Like I said, every element has a certain point where there is a critical point. So we want to actually work with an equation today, the van der Waals equation of state, and think about this in terms of A and B parameters. Break it down and solve for A and B parameters, and then use that to solve for the compressibility factor. Okay. So we can actually use the ideal gas equation and manipulate it in a way where we can work with it in terms of a non-ideal gas. So let's say we have PV equals nRT, like we know the ideal gas equation. So P equals nRT. Now in today's example, I'm going to assume that N, the number of moles, is equal to 1. So we really don't have to use this in our equation. We kind of just forget about it right now and just assume it's multiplying everything by 1. So it's there, but it's not at the same time. We don't have to keep writing it down. And so for this example, we want to actually solve for pressure in this instance and use volume, our specific volume, to solve for pressure in terms of volume and temperature here. So we can rewrite this equation and say that P, our pressure, is equal to RT over V. Now, let's use the example, you have a container. And inside that container, you have, for instance, water. Or there's a certain amount, not really necessarily water, we have a certain volume. And inside there are tiny particles, gas particles, let's say. There's no water inside, there's gas particles. And they have a volume. Depending on the size of the atom, that can vary. Vary from like sizes of argon to sizes of hydrogen, which is very small. So let's say we want to subtract from the specific volume here, which is in cubic meters per mole. We want to subtract the B parameter, which is in this case is in the same units, and it is the volume of the particles inside. So we can take this, subtract the B parameter is the volume of the particles inside. Specific, it's this B parameter is different for each element or different kinds of air molecules inside. Subtract it from V, divided by, so this is on the bottom, the denominator, multiply R and T, divide by this, and you get your pressure. Okay, so that's one thing that you think about. So this is all the same units we can subtract it from. So we also want to think that for the van der Waals equation of state, the van der Waals equation, van der Waals interactions are the weakest intermolecular interactions there are. So they are bonds. Each compound has interactions between their molecules and everything. In these cases, these are very small and they are weak. So we want to actually account for this and subtract it from our pressure here. So we want to say a certain value of A divided by our specific volume squared. So we're going to take, and now, find our B and A parameters and use that to solve for P. So we can also look at the relationship now of this equation. So we can ask ourselves, so looking at the temperature here. At higher temperatures, we are going to have, we can plot this out and look at, let's actually bring it over here real quick. I can show you a better graph representation of this. Okay. This. Okay. So if we were to plot this equation or plot at various different temperatures, it's dependent on temperature. At higher temperatures, our equation we just wrote. Actually, write this again. So P equals RT over V minus B, subtracting A over our specific volume again. So at higher temperatures, we're going to notice a trend where we have our ideal gas law here. And at higher temperatures, our line that we plot is actually going to look similar to this. It's going to be very straight, or a lot more closer to this line. And this is above the critical point. Take notice of that. So these are temperatures above the critical point. We're going to have lines looking like this. Now, as the temperature decreases, we are going to get more of a dip. So once the temperatures get below the critical point, we're going to get a dip here called an inflection point. Now this inflection point is going to get lower and lower. And looking over here, we have a better representation of all of them side by side. The lower the temperature, you notice these dips getting lower and lower. The inflection point, you're going to get more of a minimum and a maximum. You're going to see this more often. So now we've explained the relationship at higher temperatures. So we know that at higher temperatures here, we're going to have more of a straighter line, closer to an ideal gas. At lower temperatures, we're going to have more of a dip, an inflection point taking place. So at higher temperatures, we can take note that this right here, the forces that take place in every interaction, they're always present. Non-polar, polar, no matter what the charge is, they're going to be these interactions. They are almost, they mean nothing. This is, at higher temperatures, this is deemed as a more dominant trait here, a dominant part of the equation, that this is negligible. We can just forget about this on this. It's so small compared to the force of the temperature and the volume and the size of the molecules. This means almost nothing. So, then we can start looking at how do we solve for the A and B parameters. Well, first, I guess we can take, we have two parameters. We're trying to solve for two different things. We need two equations. So let's go ahead and try and say, take the first and second derivative of these this equation here and set them equal to 0 at the critical point. We want to say that our derivatives here, our two derivatives we're going to take, are going to be equal to 0 or go to 0 at the critical point and not other points. So saying if we said not just at the critical point, that these two derivatives I'm about to write are equal to 0, that means the entire thing at any point is going to be a horizontal line. It's just going to be our derivatives, our first derivative, and our second derivative, are just going to be a horizontal line. And that's not what we want to take note here. We do not want this to be a thing. We want to plot them. We want to say just at the critical point, we want to set them equal to 0. All right, so we can take the first and second derivative. So let's say dp over d. So this can be the first derivative. d of b equals, let's see, negative r times temperature divided by our specific volume minus our volume of the molecules squared plus 2 times our A parameter over our specific volume cubed. Okay, that's our first derivative. So now we can go ahead and try and solve for our second derivative. So second derivative is going to be dp, so here, b squared equals, okay, so we're going to take up our 2. So that's going to be positive now. So we have 2r times our temperature over our specific volume minus our volume of our liquid, our moles, or atoms, cubed, minus, this is going to go to 6a over v to the 4th power, our specific volume. And we want to make sure we evaluate these at our critical temperature. So right now, these are just in terms of just the entire, not just at the critical temperature, they're just at everything, at any temperature, or a critical point, per se, not the temperature. So we want to actually evaluate this at the critical point. So let's say we go up here and make sure we evaluate these at the critical point. So let's say d p over d evaluated at critical temperature, critical volume, and the critical pressure. So this goes to minus r times critical temperature over the critical volume minus v squared plus 2 times our A parameter over our critical volume. I think this would be cubed. Yeah. And we'll do the same thing up here for our second derivative. Our critical volume, critical temperature, and critical pressure. So we can say our second one, which we had to be not negative. This is not negative. I need to change this real quick. All right. So that's not negative anymore. So it's 2 times R times our critical temperature over critical volume minus B, the volume of all our particles, cubed. Okay. This goes to a negative now. 6 times our A parameter over our critical volume to the 4th. So now actually we are ready to set up and start solving for our A and B parameters. So let's actually go ahead and start doing that. So to solve for our B parameter, I'm going to, so let's do this. So we can actually go ahead and divide this by 2. Bring this down to 1 and this down to 3. It'll make it easier to solve out later. So now that we have that, we can actually go ahead and move forward, taking the reciprocal of this multiplied by the top portion, reciprocal of this multiplied by the top portion, and then set equal to each other, and then solve for B. Then we'll take whatever we find for B, plug it back into the original equation up here, and then just solve out for A. Okay, let's start by taking the, let's take the reciprocal of this, so it's VC, our critical volume, minus our B parameter, cubed, sorry, that's wrong. Let's see, that's cubed over RTC, our critical temperature, times RT, critical temperature over here, and then our critical volume on the bottom minus or B parameter squared. Okay, so these cancel out, and actually these cancel out too. So now this just goes to VC minus B plus whatever we get from the reciprocal here multiplied by this, simplified out, equals 0. Okay, so let's solve for this part now. So let's go critical volume, fourth power over 3A times 2A over critical volume cubed. So this cancels out, this goes down to 1, A's cancel out, this goes to then critical volume times 2 over 3. Take this, plug it in up here, so 2 over 3 times your critical volume. So now we can actually start solving for B. Okay. So actually, let's go ahead and erase this and make some room. All right. So actually, we can go ahead and erase this too. We'll need a little more room here to solve for A and B. So we have our volume minus B plus 2/3 critical volume equals 0. Okay, so now we have this, we can start solving. So we can move things around now, set them equal to each other. So this would go to our VC minus B equals negative 2/3 critical volume. So actually we can go ahead and switch the sides on these. Since these have the same units, we can start, this is technically like 3 over 3. And if we add this, this wouldn't be negative. This would be negative. Yes, this is negative. There's negative here, we try to do that. Okay, that makes sense. Alright, so this is negative. We add over, we have a positive now. So if we switch sides on both of these, we can then simplify it down. So, and solve for B. So this is typically 3 over 3 minus 2 over 3 VC equals 1/3 VC. Switch the side on this, bring it over here. This comes over here, equals B. So our B, we just write up here, B equals critical volume over 3. Okay, so that is our B parameter. We solved that for now. So now that we have that, we can actually plug this back up here into our top equation, our first derivative, and we can solve for A by plugging this back into B. All right, so let's go ahead and do that. All right, so we have negative R times the critical temperature over V, or critical volume, minus a critical volume over 3, and this is going to be squared. So if we're going to square this, we need to make sure we square the entire thing. So we can actually simplify this down to, this goes to 2/3. 2/3 squared is 4/9. So 4/9. And we are going to want to, let's see, take a reciprocal of this, flip it around. So now this becomes, this entire thing right here becomes, let's see, it's going to go to, it's going to go to 9 RTC, sorry, my handwriting's not very good, over 4 BC. Okay, so now that we have this, we can go ahead and set this to the other side. So minus equals minus 2A over BC VC cubed. All right. And this actually squared. Forgot that. So that's squared now. So we can actually go ahead and cancel out, since these are both negatives, we can cancel that out and make it positives. So we're going to try and get A by itself now. So we can move this to the top here by multiplying. Move this to the top here by multiplying. And let's see, we can get, actually we can leave VC here and just take the 4 up. And just multiply that up there. So this goes to, actually we can bring this down to here and make this 9 over RT VC cubed over VC squared equals 8A. All right, so now this cancels out, goes down to a 1. If we divide this by 8, we have A, or A value, equaling 9 over 8. I'm trying to make this a little bigger for you. This goes to 9 over 8 R times our critical temperature times our critical volume. Yeah, that's A. Okay, so now we have our A and B. We solve for A and B here. So now that we solve for A and B, we can actually plug this back into our original equation and solve and try to get our, we want to try and solve for our compressibility factor. So let's go ahead and plug this back into our original equation up here. So let's do that. I'll make some room here. Write my first derivative. Now remember, we are in critical. We're thinking about this in critical terms, so we need to change these values critical. So now we know A and B. We're going to plug this back into our original equation. So we now have B equaling, what was it? It was critical, so our critical volume over 3. And we have our A value equaling, it was 9 over 8 times our R value times critical temperature value times our critical volume value. And actually this would, I can erase this. Put the 8 down here, 9 up here, RTC, VC. So I can go ahead and actually simplify this. Take out the VC here, take out the squared, simplify it down. And I can change this by subtracting it from VC, so they're the same units right here. Let's go ahead and do that. So let's take, this goes to 2/3 VC. All right. All right, so it's 2/3 VC. And we want to make sure we flip it around and put the 3 on top and the 2 on the bottom. And keep the VC on the bottom. So let's bring the 3 on top, 2 on the bottom, VC. Okay. So now that we have, you notice here, we actually have all the units being the same. So really all we have to do solve for the pressure or our compressibility factor is really take 3/2 subtracting 9/8 and it'll give us our compressibility factor. Okay, so let's go ahead and do that. So 3/2 minus 9 over 8 times everything has the same units times our critical temperature over our critical volume. So we need to get these in the same units, same denominator. So what do I need to do? I need to get these to the 8th power. So get these to 8. So multiply this by 4, multiply this by 4. So this goes to 12 over 8 minus 9 over 8. And this goes to 3/8 VC on the bottom, critical volume. R times the critical temperature equals P. So in this case, this is in terms of critical point. So this is for gases that are not ideal. This equation is for non-ideal gases. So, or gases that follow the van der Waals equation of state. That's a more accurate statement. So this is for the van der Waals equation of state at critical points. Critical temperatures, critical volumes, critical pressures. So if we take 8/3 is actually our compressibility factor, we can move this around by doing, so this is really our compressibility factor for a van der Waals equation of state is 8/3 equals P. Bring this to the top by multiplying everything. So critical volume, volume there, and then divide this on the bottom. So R critical temperature. This is our compressibility factor here for our van der Waals equation of state, 8/3. Now, this is actually the relevance of this. This compressibility factor, is the same for any compound gas that has a similar function of that follows the van der Waals equation of state and has those interactions. So this is true for any compound. This is the same value. That's why it is so relevant. It is usable and reusable for any of those interactions that are the same as the van der Waals equation of state. Now, for ideal gases, your compressibility factor is going to be equal to 1, actually. And this is actually summed up by the universal symbol of this is Z. This actually stands for compressibility factor. So Z equals 8/3, our compressibility factor. For a van der Waals. So van der Waals equations only, this is the 8/3. This is what we're looking for, our compressibility factor. Now for ideal gases, your compressibility factor is always going to be 1. And it's going to be 1. Yeah. Equals our pressure. And notice how this is at values not at the critical point, ideal gases. All right, so we have now solved for A and B parameters. We know that A, looking back here, is 9/8 R critical temperature times our critical volume, and our B parameter is equal to our volume critical over 3, and our compressibility factor is 8/3. And the relevance of this is that it is the same for all gases, or all gases that are like the van der Waals equation of state. All right, thank you for watching my video. Have a great rest of your day.